Hey tubers, Daniel here. Today I have for you what I consider a very interesting video about spaceflight, and in particular about orbits, orbital mechanics, orbital maneuvers, and just generally using orbital science to, say, go to Mars. That's right, we're going to Mars. This program that I'm using here is called Orbiter, and Orbiter is a space flight simulator, and this is one of my favorite programs of all time. Yeah, so our Orbiter is sort of a hardcore, very technical simulator with lots of buttons, lots of ways to die, but it really is sort of the ultimate platform for exploring and understanding space travel, so that's why I'm using it. As far as the audience for this, I'm not really sure who it's supposed to be. I'm just kind of doing this for fun. I thought others might find it interesting. If you're new to Orbiter and trying to learn it, it might be somewhat instructional. I do some basic orbital maneuvers, and later on we do some docking as well. And later on we use the Transx MFD to plan our trip to Mars. So if you're trying to learn that, I'll go over some of the things that tripped me up, because I recently had to relearn it. If you're trying to look for more of like an in-depth, very like more verbose and very technical instructional, then go ahead and check out David Courtney's channel, and I got him down in the description. I used his videos to get past some of my own obstacles, and I highly recommend watching his videos if you really want to learn Orbiter. Either way, you kind of need to read the manuals front to back. I've easily read hundreds of pages of PDFs just to do this. If you're an advanced Orbiter user, then please feel free to point out any mistakes, or if you want to critique my technique, that's fine. Mostly, I just think this subject is very interesting, and I hope to entertain first as well as to inform. So, yeah, any audience that's interested in spaceflight should stick around, because it's for you. So, yeah, right now I'm currently docked to the Mir space station, which, little known fact about this, funny or tragic depending on how you look at it. The Mir space station was actually destroyed in a crash, a spacecraft crash. The Russians were trying to manually dock to it. I think either the automatic system was down or they were just feeling Russian. But in any case, they collided with it and did enough damage to it where it wasn't completely destroyed, but there was enough damage to it where it was deemed sort of impractical to try to repair it because of cost and reasons. Yeah, so I'm docked to the Mir space station here, which is obviously still here in Orbiter, even though it's completely destroyed now, burned up in the atmosphere. So undocked with Mir, I'm going to do some orbital maneuvers just to show you some basics of how orbits work. And then we'll try to rendezvous with the International Space Station, the one that's still there, hopefully for a long time. And we're going to dock to the International Space Station. And as part of the fiction, I'm going to refuel the spaceship and get more oxygen and nitrogen and, I don't know, toilet paper, toothpaste, all the things you need on a year-long journey. Yeah, and then after that, I'm going to plan a burn to Mars. And then at a couple points during the flight to Mars, we'll do some mid-course corrections and have a nice, perfect capture into a low Mars orbit, and then we can check out what Mars looks like. So lots of fun. So yeah, so first off, just some caveats about what's going on here. My spacecraft here, this is the Delta Glider 4, and this is a completely fictional spacecraft. Its propulsion system and the amount of fuel it can carry is impossible, basically, for chemical rocketry. It's much more efficient than it's really possible. It's much simpler than any spaceship. But you'll see it's actually got a lot of buttons here. Let me show you real quick. It's got all this stuff here, all this life support stuff, cool sound effects, all this fuel management here, gas management here. You can control inner and outer door lock doors, nose cone opens and closes, an entire electrical power system. So it's got a lot of stuff, and it's a lot of fun to use. The main tools are really these things down here. These are the MFDs. There's one for orbit. There's one for surface. This is a map. And so these are the main tools that we'll be using, whereas these are more like sort of just kind of embellishing in the simulation of the fictional spacecraft. Another thing I can do is I can accelerate time in Orbiter. Let me show you here. Right now I'm at 1x, and I can increase that to 10x or 100x. So spaceflight is fundamentally time-consuming. You hear about the Apollo is like many days to get to the moon. Going around one orbit of Earth is around 90 minutes, and then going to Mars can be years. And so the simulation wouldn't be much fun if you had to wait for a year to get somewhere. And so we'll be spending actually the majority of the actual flight time will be spent at like 100,000 times acceleration, which is about a day per second, just to put that into context. And also some technical limitations of Orbiter itself that I just find interesting. The mathematical model is based on Kepler's laws of planetary motion, which is it's limited to only calculating two bodies at one time. So, for example, my spacecraft and the Earth, or the Earth to the Sun, or the Moon to the Earth. But one thing it can't do, just for example, is if I'm in an orbit around Earth, technically the Moon's gravitational force is going to have some influence on my trajectory. But Orbiter simply can't do that. It only knows about the gravitational body that currently has the most influence on you. So that doesn't really, in terms of the experience, I don't really think it changes it that much. There's a couple times during the flight to Mars you'll see where we transition out of the Earth orbit into the Sun orbit. And it can be a little bit confusing, and it's not really well explained in the manual. But I managed to figure it out, and you can kind of work around it, and it's only a few little things you kind of have to know, so it's not too big of a deal. Orbiter also has no idea about relativity. It does do some. It has options for turning on like gravitational perturbations, which, for example, non-spherical gravitational forces, and there's a couple other ones that I'm forgetting now. There's various types of like precession and errors that get introduced from other forces, but it has no idea about relativity. And to be honest, I don't think it matters that much. I was told once that even in NASA's planning for really long-range interplanetary missions, they don't need to think about relativity because it's just not enough of an influence to matter. There's so many other places for error that that's kind of a small, insignificant one. But it's interesting to note. And of course, the limitation that NASA has to deal with is the communication latency between where we are now and wherever the spacecraft is. It can be like minutes, hours away in terms of communication. But we're not doing anything remotely in the simulation. We'll always be in the spacecraft, so that won't matter for us. So yeah, let's go ahead and get started here. All right, so I like to start this in a cold shutdown mode where everything's turned off, just for that sense of realism. So first things first, I'm going to go ahead and get my electrical power started up. I can go ahead and turn on these modules here because I already have voltage on the external power unit. Go ahead and close my airlock doors here, both the inner and outer airlocks. Hydraulic pressure is off, that's good. Okay, go ahead and turn on both generators. So the APU is an auxiliary power unit. It basically just runs off of fuel and converts fuel into electricity, because a lot of the ship runs on electricity. Go ahead and turn on both MFDs here. And let's see, get both the primary and backup life support systems going here. Disconnect the external interface for my life support system, replenishing system. Okay. I'm going to turn on all the valves for the various different thrusters I have. Go ahead and open up both the retro door and the hover door. These are basically just doors that allow the spaceship to thrust in hover and also in retro, which is backwards. Normally those are closed for re-entry because if they're open, it's a vulnerability and it can burn up because the fact that it's exposed. I'm also going to deploy both my long-range antenna and the external radiator. And can you see it? Yes, we can. So the long-range antenna is just sort of an orbiter feature where you can get some telemetry on a target, distance and your relative speed. The radiator is kind of interesting because so like normally when a spacecraft is going through space, especially if it's on a interplanetary mission, it's just going to be sitting there baking in the sun. It gets really hot, and so it's going to be absorbing a lot of energy. And so this radiator is basically a way for it to just kind of shed off some of that thermal energy. It doesn't work with air, obviously. It's just infrared, but I thought it was interesting because it's a little bit like a car almost. Okay, so I might be ready for undocking here. Let's go through the checklist. Checklist for undocking. Okay, I didn't turn the strobe and I need to turn the EPU off. So external power unit, that's like the electricity that would be coming from the Mir space station. So there's an interface there, it has to be disconnected, otherwise it would break. And over here, should have done this earlier, go ahead and turn the seatbelt sign on, or turn it off and then back on. Hit the bell, get my crew's attention, so they will be ready. And then turn on the strobe, which is just basically a safety feature so that I can be seen in space. Okay. Let's do another check.
Configuration correct.
All right, so I'm ready to undock now. Undocking in 3, 2, 1.
Undocking confirmed.
Cool. So you can see from this external view, I'm slowly moving away from Mir. All right? And so the next thing I'm going to do is I'm just going to put some distance in between my spaceship and Mir. We wouldn't want to damage it.
Translation.
So I'll turn on translation mode, which means I can use thrusters on the spaceship to move linearly, like up and down or left and right, forward and backwards. And I'll just do some reverse thrust here. And you can see in this external view, that's the thrusters turning off, on and off there. I'm thrusting away from the Mir. Okay. And and then next I'm going to just put myself into an orientation where I can turn on my main thrusters and just put some distance in between myself and Mir. We wouldn't want to relive that experience where we accidentally crash into Mir like the Russians. Okay. So don't pay too much attention to this right now. I'm just trying to get some distance to set everything else up. But you can see I'm kind of sideways in my orbit. Okay. So there goes Mir flying away. You can see it. It's a pretty unrealistic amount of thrust the spaceship has, but that's all right. Okay, so what I want to do next is explain the orbital MFD. So that's this MFD right here. And so what's going on here is there's a gray circle, there's a gray inner circle, and then there's a green outer circle. The gray circle is the surface of the Earth, so that's the Earth itself. And then the green circle is my spaceship's trajectory around the Earth, like that. So you can see I'm sort of constantly above the Earth by some amount there. In fact, that amount is around 300 kilometers up in the air, so 300 kilometers from the surface. All right. So for any orbit, there is a place where the orbit is closest to the ground, where the altitude is lowest, and then a place where the altitude is the highest. And those 2 points are called the periapsis and the apoapsis. So these 2 numbers right here on the MFD, this top one is the periapsis, that's PEA. That's a periapsis altitude. It's 282 kilometers up in the air, and the apoapsis is 312. So what I want to do right now is I'm going to change my orbit. Actually, let me show you this first real quick. I'm just going to warp time ahead so you can see this moving. That's my spaceship moving in its orbit. The distance between the green and the gray there is my altitude. And otherwise, this line is showing me where I am in my orbit. All right? Let me get back in the sun here. Okay? Boom. All right. So what I want to do now is I'm just gonna change my orbit into a more exaggerated ellipse so I can explain this periapsis and apoapsis a little better. So the way I'm going to do that is the way I'm going to change the shape of my orbit is I'm going to point my ship in the direction that I'm traveling. It's going to take a second to maneuver around here. This little plus sign in the HUD here is telling me where, it's basically telling me where like forward is, like what direction I'm actually going. That's my direction vector relative to the Earth, of course. All right, so I'm pretty much settled here into my orientation, and all I want to point out here is that I'm pointed in the direction that I'm already going. So when I add power, it's going to make me go faster in the direction that I'm currently going. Okay. The fact that it's on the side like this doesn't matter. All that matters is which direction the thing is actually facing. Okay, so let's go ahead and do a full throttle burn here. And over on this side, over on this MFD here, just take a look at what happens to the shape of the green line. Remember, the gray line is the Earth. That's not going to change. And then the green line, as I'm firing my thrusters over here, it's going to make a change. So here we go. All right, so maybe what you can tell is as I'm adding more energy to my orbit, the altitude on the opposite side of the orbit is getting much, much higher. In terms of my altitude as where I'm at right now, that's actually not changing at all. Just a very small amount. So what's interesting about it is that if you want to change the shape of your orbit, you make a burn either forward and reverse, and it changes the altitude of the orbit on the opposite side of the planet or whatever body you're orbiting. It changes the altitude up or down. And so what you can do, so maybe what you see in this case is that we have a slightly elliptical orbit. The Earth is obviously perfectly round, but our orbit now is elliptical. It's close to the Earth here and really far away here. And so the next maneuver will be to circularize this orbit, more or less. We're going to get it kind of close, so that I'm always the same distance away from the Earth. So it'll look like 2 circles. So I'll go ahead and warp time now to 100 times. And remember how I was saying whatever change you make on one side affects the opposite side. So I'm going to go to the opposite side. And in fact, this little tiny little dot here, that's the opposite side. And these numbers over here will tell you how far away you are from there, if you want it in terms of time. And then some of these other numbers are, for example, the periapsis altitude is the altitude at the periapsis, which is on this side, and the apoapsis, which is the altitude on this side. So I'm going to get sort of close enough here. Three, two, one, mark. Oops. All right. So now I'm affecting the side opposite of me now here. So I'm making that orbit bigger on the other side. I'm also circularizing it. All right, so there you go. That maneuver, basically those two burns. The first one increased the altitude on the apoapsis side, and then when I got to the apoapsis side, I did another burn in the same direction, forward, and that increased the altitude on the periapsis side. I'm doing a little bit more right now because it's not quite circular. And so the effect is I've changed my orbit from a low 300-kilometer orbit, was what it was before, to now it's 2,000 kilometers. So much, much farther away from the Earth. It's a little bit tricky to do conversions here because like everything in Orbiter is very, very metric. So everything is in meters, but sometimes you get something like this right here, this periapsis altitude will be 2.07, and what that's saying is megameters, and so you have to divide that by 1,000. So it's 2,000 kilometers. Ugh. Okay, so there you go. That's the orbit MFD. Obviously, all these numbers mean something. Usually, I'm only sort of paying attention to 4 or 5 at a time. But it's interesting to note that you can understand orbits in a two-dimensional view. All orbits are in a particular plane. So if you want to change the shape of your orbit, you can do so without needing to understand how it's working in 3D. You just have to see it as a 2D projection. All right, guys. For this next part of the video, I want to rendezvous with the International Space Station. I've made some adjustments here. I've changed my orbit back to a reasonable low Earth orbit, so we're similar to where the space station's at. And I just want to go through each of the steps, excuse me, to rendezvous with the space station. All right, so down here in my orbit MFD, I've just got myself right now. But what I can do is I can add the International Space Station as a target. And so on the left side is my ship, and on the right side is the International Space Station. Once again, the green line is my orbit, and the yellow line is the International Space Station orbit. Now, you'll probably notice right away here that the orbit of the space station doesn't make any sense. It looks like it's going through the planet. Well, what you're actually seeing there is that the International Space Station is on a different orbital plane. If we change the projection here, now we're looking at the International Space Station, and then the green line looks weird, right? That's our ship. And so what's going on here is we're on a different orbital plane, and I found this thing. I thought it might be a good way to explain orbital planes. If you imagine each one of these lines going around, each one of these circles, that can be an orbit. So this is an orbit, and then also this is an orbit. And what you'll notice is every single one of these orbits, they intersect each other. So take this orbit and this orbit. Well, they intersect right here. And if you look at it straight on, you can see it. And each one of these is a different orbital plane. And right now what's going on with our orbit MFD is our orbit is the one on the outside, but then there's this other one that's like this, and we're not looking at it straight on, so it looks like an ellipse, right? So that's what you're seeing over here in this orbit MFD. You got that ellipse right there. And then you've got the big circle, which is us. And so what we need to do is we need to change the plane of our orbit. And the way we do that is we basically put turn the ship either left or right, depending on which way we need to go. And then right at the point when our orbit intersects our plane intersects the plane for the International Space Station, we're going to thrust like left or right, depending on which way we need to go. And then that's going to make us turn and intercept that plane. And so there's a special tool in Orbiter for that, and it's called Align Plane. So that's what I'm going to use right now. Let's go ahead and set the target to International Space Station. And so here it's telling us the relative inclination is 77 degrees. And if you look at an example again, if you look at this here, the relative inclination between this guy and this guy is 90 degrees. The relative inclination between this one and this one is 45 degrees. So our relative inclination to the space station is somewhere in between those, which means we're pretty far off plane from the space station. But we've got enough fuel to make this happen, so let's just do it. And the way this works, this tool is kind of interesting. It's an abstraction of what's really going on. And what you have to do is, here, let me fast forward here. So this is us right here, going around. And this line right here is analogous to the plane on here. So as we approach the point where our plane intersects the other plane, that's when we need to fire our thrusters. Okay, so we're coming up on our burn here. We're approaching our burn. So this number right here, these numbers down here are the amount of thrust it's going to take to do our plane adjustment, our plane alignment. And that's a pretty long burn. That's almost 1,300 seconds is what that is. And then this Tn is the countdown until we reach the descending node. And I know from experience that when this number is basically roughly half this, that's basically when you start the burn. So we're coming up on the burn here pretty soon. Let's see, half of 13.65. Okay, so right about 650 seconds we can start the burn. And then I'm going to point out two things to sort of pay attention to. And in fact, I'll go ahead and get it started a little bit early. So just make sure I have plenty of time. Okay, so start the burn. And so I'm pointed left. If you notice how I'm pointed in relation to how I'm moving, I'm basically pointed exactly left. And so the effect that this is going to have is it's going to change my plane around. It's going to sort of pivot around where my ship is now. And if you look real closely, you can kind of see that my direction is sort of curving here. All right, it's kind of subtle. And let me slow that back down. And the other thing I wanted to point out here is over here, this ellipse is becoming more like a circle, and that's the International Space Station orbit, you remember. And it's not because the International Space Station orbit is changing, of course. It's because our plane is becoming more closely aligned. So at the end, when our planes are perfectly aligned, this will be a circle just like ours. The ISS has a mostly circular orbit as well, so it'll look like a circle. All right, so see, I got a little bit ahead. A lot of this is just looking at these numbers and kind of counting down to when you're supposed to burn, and just a lot of timing stuff. And luckily you can warp time, which makes it easier. But it's really easy to overshoot, and so, like I just did there, because I was talking too much. Yep, so there I am. You can see it in daylight a little better here now. And it's hard to see, but it is actually slowly rotating. The whole thing's slowly rotating. So it looks like it's going to take me at least 2 tries to get this aligned, which is fine. It usually takes me about 2 or 3 times. And so you can do half your burn before you get to the sending node and half your burn after you get to the whichever node you're approaching there. And But I found out if you start the burn much earlier, I noticed that if you just do it when this is half of that, you can actually do it in a single burn. And I think it's probably actually less efficient that way. I think this tool is optimized for efficiency rather than speed. But we do have a lot of fuel. We're prepped for a Mars flight, so we got lots of gas. And we're going to refuel at the ISS anyway. Okay? All right, so let's see if I can get this last. I'm down to 5 degrees, and you notice over here, the ISS already looks mostly like a circle here. But we're still about 5 degrees off. And you can get this down to 0.00, which basically means less than 0.005 because of rounding. Okay. And so this time I'm approaching the ascending node, which means I need to point myself in the anti-normal direction. Go ahead and do that. And so, yeah, again, once this number is half of that number, then I can do it. It's going to be approximately 26 or so. Let's see if I can get it perfect this time.
Rotation translation.
Yeah, this is good. I'm just above half. And as long as you stay above half, you start the burn just before half, and then as long as you stay above half, then you can do it in a single pass. You can see my degrees coming down now. I'm at 2.5. Okay, actually getting a little bit ahead there. Very, very close. 1 degree. Okay. That's pretty good. It could actually be a tiny bit better. Both these numbers, like the relative inclination is 0.00. It's as close as the instrument is really telling us we can get. You can actually get a little bit closer, and you know when you're as close as you can get when, see, as I go back and forth, it looks like it's kind of balancing this thing. You can get close enough to where it won't even, like it just goes right past it. So anyway, it's definitely really, really, close enough. So yeah, let's take a look at the orbit MDF now. Now that we've solved the plane problem, we also need to actually rendezvous with the International Space Station. So even though we're on the same plane, we have different orbits, and so we're gonna play with our orbits until we can either catch up or fall back behind. And so let's look at where we're currently at right now. The International Space Station is about 350 kilometers, and we're actually pretty close. I have a more elliptical orbit. I have a close approach of 220 kilometers and an apoapsis altitude of 428 kilometers. But the biggest problem is that, so here's the International Space Station, this line, right, and its orbit, and ours is over here. You can kind of barely see it. But that means we're sort of like really way behind where the space station is. And you might think it's as simple as just like speeding up to try to catch up to the space station, but the problem is, as we speed up, remember that increases the altitude on the other side of the orbit, and the larger the orbit is, the speed is not necessarily different, but because it's such a larger circumference, it just simply takes a longer time to cover that distance. And so what we actually have to do is either speed up to slow down or slow down to speed up. And this is one of the things that's really interesting about orbits. So there's an instrument that we use here. It's called a Synchronized orbit. Sync orbit. And let me get the International Space Station here. And what this is telling us is that in the next 5 orbits, the closest we're going to come is this yellow one. This yellow one means it's the closest encounter. And this DT min is telling us the number of seconds that's in between when I pass a position and when the ISS passes that same position. So this is actually really bad because this is almost 2,000 seconds. And what that means in terms of orbit, it's essentially 2/3 of an orbit. This is me, this is the ship, and here's the International Space Station. So there's two ways we can get closer to the International Space Station. The first is we can adopt a smaller orbit so that we're slowly catching up, because we'll have a smaller circumference, or we can take a larger orbit and it will be catching up to us. And so in this case, I've just discovered through trial and error that it's actually difficult to catch up to the International Space Station or anything in orbit if it's kind of far away. And the reason is because it's already in a pretty low orbit, and so for us to take an even shallower orbit means we would be getting dangerously close to the atmosphere. And in fact, I'd have to. The lowest I can kind of go safely is maybe 150 K, which is just not enough to make that much of a difference. So it would take a really long time to catch up. So we're going to do the opposite, which is we're going to actually slow down our orbit. We're going to make our orbit bigger, and then it means it'll take us a longer time for us to do our orbit, and the International Space Station will continue in its orbit that it has now, and it'll be slowly catching up to us. So let's just give that a shot. I want to make my orbit larger, and that's the same operation I did earlier in the video. I just made my orbit much larger. Okay. So I get myself into a prograde direction here. Unfortunately, you can't see anything. And I think what I'm going to do actually is I'm going to keep my periapsis close to the ground, and then just to increase my apoapsis. So the effect is still that the orbit is going to be much, much larger, but the difference is I'll still be coming in a low orbit, and that gives me an opportunity to rendezvous with the space station. Another way you can do it is to take a large orbit and circularize it and wait until it looks like the space station is catching up, and then change to an orbit that's elliptical. But let's see if we can do it in one shot. So I want to go to my periapsis point in my orbit, which is 3,000 seconds from now. So let's go ahead and jump ahead. Okay, 40 seconds. Let's get back in position here. All right, and this actually jumped past, it went to 0 and then it reset, but that's fine. I mean, we're close enough. All right, and then let's start making our orbit bigger. So, I don't know if you saw it there or not, but this number is now getting much, much smaller. And what's happening is the computer is just simply making an estimation that this is how close we're going to be. And I bet I can get it pretty close here. All right. So now what it's saying is and this is still a pretty long time, so we'll have to warp ahead fairly quickly. But the DT min is now 0.02 seconds, so 20 milliseconds. So in reality, the International Space Station is going to pass a position, and then 20 milliseconds later, I'm going to pass that same position. And that might not sound like very much, but again, right now I'm traveling 8.1 kilometers per second. So that's a fairly good rendezvous, and that's what we're going to go with, but it's not quite perfect. Okay, so let's just play some cards until the time reaches. And I'll probably do one more aligned planes as well, as we do these burns, you introduce a little bit of thrust in on the sideways direction, and it just kind of slowly throws off your alignment. So I'm two orbits away or so right now. Let's check out aligned planes. We're still quite close there. Certainly close enough. Alright, so let's change this to sync orbit so we can see both these things at the same time. And then I'll try to make a correction here on the ascending node for the plane alignment. Here, watching this number. 3. All right, and there we go. So this is what I was talking about earlier. As I'm trying to balance the thing, it doesn't even show the middle point because I just go right past it. So that's great. That's an almost perfect plane alignment. I can't really get it better than that. All right, and let's get back in the prograde direction. So if you notice, there's just kind of a lot of refinement to this rendezvous that I'm doing here. DT-min is 350 milliseconds. That's pretty good. Let's make it even better. I can do it's a little bit more precise now that it's closer in time. I can have a little more granularity in this number here. Oh, 0.0. Okay, so we are very close. We still need to wait this amount of time, but it looks like we're very close to our rendezvous. So next thing I'm going to do here is I'm going to go ahead and set up my comm radio here. Tune it into the International Space Station's transponder frequency, which is going to give me telemetry as we approach. And it'll also allow me to use the heads-up display to see where the International Space Station is and our closing velocity, and it'll show me the vectors in the heads-up display for the towards and away vectors. And those are basically what you use for the final rendezvous maneuvers. So let's see, 131.4. Okay. And go ahead and turn on my docking MFD. I haven't showed you this one yet, but this one is basically the tool that you use for the final docking procedure. And we're not within range right now. You can see we're on the green line, and the International Space Station is on this yellow line, and we're just over 1 orbit away. So let's go ahead and move forward in time here. You can see we're ahead of the International Space Station right now, and now it's catching up. And on this final orbit here, we're going to intercept it right here. Okay, so, why don't I have let me go check my comm, make sure I got the right frequency. 131.3. There we go. Docking thing. And there we go. And I can go ahead and put this information on the heads-up display. Okay, so we've got a very fast closing speed, almost 600 meters per second right now. This circle right here, that circle is telling me my direction vector relative to the space station. So you can see that I'm almost going directly towards it. And this will probably come down a little bit more as we get a little bit closer. And then if you look the other way, there's the direction vector in the opposite direction. And so what we're going to do is we're going to get a little bit closer here, and then I'll probably try to time my burn for about 1 minute before the intercept time. And I'll point my spaceship perfectly in this direction here with the opposite direction vector. So let's go ahead and get that prepped up.
rotation.
Oh, my joystick's not plugged in. All right. Let's get that. All right. So this closing velocity is much, much higher than I'm really comfortable with. The reason it's like this is because we were doing sort of a weird orbit where we had a really extended apoapsis. We were going really far away. And then on the inside, we were coming in really close to the Earth. We were at 200 kilometers, something like that, whereas the space station is 300 kilometers. So I'm just going to be going a lot faster than the space station. And that makes this final maneuver sort of difficult because, well, you have to do a really long, powerful burn, and it just makes it a larger opportunity to make mistakes and not be pointed in exactly the right direction. But we'll give it a shot. Don't have much choice at this point. All right, so we're at 2 minutes right now. I want to get that lined up as best as I can. Okay. Sorry, I was a little over 2 minutes there. And now I'm coming up on 1 minute. 86 seconds. So I'm going to make my burn at 60 seconds, so 20 seconds from now. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, burn. It's a very critical maneuver here. Closing velocity is coming down pretty quick. That's good. I'm at 30 kilometers from the International Space Station. I'm basically going to do this burn until the closing velocity levels out. There's a good chance that we're not going to, be real precise in our approach. So that closing velocity is going to go down, and then all of a sudden it's going to start coming back up because that means we've slightly missed it. But that's okay. So what we're going to do is we're going to do that maneuver. Oh, there we go. Got pretty close actually. Let's go ahead and change this to map. I want to see how much daylight we have. Not a whole lot. That's okay.
Transrotation.
So my closing velocity right now is negative 1 meters per second, so basically there's no velocity between us. But I'm 20 kilometers away still. So what I'm going to do is I'm just going to point straight to it and then fire my thrusters. Actually, before I do that, I'm going to set up there's basically like a heads-up display for each dock. There we go. And that's going to let me see, it's going to show in the heads-up display some little like red squares. And then those, I'm basically going to line up with those squares. And I'll show you what I mean when I get there.
Translation rotation.
All right. So we're going straight for it right now. Let's speed that up a little bit to 100 meters per second. Good. And I'm going to jump a little bit ahead in time here. Normally this procedure on the International Space Station, I don't know if you've ever watched it in real time, but it takes like hours. So this is a very, very sort of hacky, very dangerous way to do it. but that's all we have time for in the video. So, okay.
Transrotation.
10 kilometers and closing very quickly. By doing these real small rotation movements, I'm actually able to I'm able to change my direction a little bit. I'm actually doing a retrograde burn here.
Translate rotation.
It's a little bit difficult to explain, but when you're facing forward and you're braking with your reverse thrusters, if you point sort of in the wrong direction from what you think you need to go, when you're braking, it actually makes you go the opposite direction. Okay, so 50 meters per second, 7 kilometers. Okay, still going to be almost 2 minutes there. Get a little bit closer, a little time warp. 4 kilometers, 3 kilometers. And let's go ahead and slow down now. Perfect. All right, just past 3 kilometers. I'm at 22 meters per second. And so I can't really... Oh, yeah, there we go. So I'm trying to aim for the end of this is kind of like the runway here. These squares, they're just alignment indicators. Okay, 2 kilometers. I'm going to jump ahead just a little bit now, again. Alright, so there's the space station, and we're going to have another look at it, so don't worry about missing it for the time being. Just trying to get this lined up. Yeah, that's good. In fact, trying to save some time here. I'm not going to use the whole runway, just going to use part of it. All right, good.
Translation. Rotation. Translation.
There it is. And you can see the dock we're going to use is right here. All right. This is probably the sort of hardest part of Orbiter, other than TransX, which I'm going to show you later for getting to Mars. But this is pretty tedious, and it's taken a lot of practice to be able to do this part. What I'm trying to do right now is get in the middle of that runway. Okay.
Rotation.
This is about to make a lot more sense in just a second here. Shit, where'd it go? Okay. There it is. Okay. No, that's the wrong direction. Problem is I'm zoomed in too far. Usually I do this with pretty far zoomed out for exactly this reason. You kind of get spinning around and you lose track of where you are. There we go. Okay.
Translation.
Alright, so there's... Let me just slow down here just a little bit.
Rotation.
There's two parts to this MFD over here. The X part is your rotation. So when I move to the right like that, the X goes closer to the center. And then straighten it up like that. And what that means is basically the the direction of my ship is going to be aligned like with the dock. The dock is like this, and then my ship's going to go... but you have to be like perfectly aligned. And then the other one here, this little yellow plus sign, that's the linear position. So if I come in too low or too high, it's telling me that. So there can be a rotation error and there can be a linear error like that. And so that's what these two things are telling us here. And so, initially what you do is you set up your rotation first. It's usually what I like to do. Just little fine-tune adjustments here until that X is right in the middle.
Translation.
And then switch to translation mode. And then it actually gives you a little helpful arrow there to tell you like if you're going towards the plus or not. So remember, the plus is the linear, the X is the rotation. So, all right. So I can pick up some speed now. And then I'll just try to nurse those two things right to the middle. And again, I'm doing this really, really fast. This would be a totally unreasonable way to do it in real life. This is probably how the Russians, crashed into Mir. Okay. So I'm pretty much dead in the middle there. That's good. And you can also tell just by looking at, where this plus is. The dock is here. The plus is usually sort of just above it. And so in the final stages, I'm just kind of looking at where that thing is. And Orbiter will let you dock up to, I think it's 2 meters per second closing speed. I find that pretty unrealistic, and so I generally try to get, as low as I can right at the last minute. Right now I'm at basically 0.7 meters per second, which if you think about it is actually pretty fast still for two gigantic machines coming together like this. Okay. Down to about 0.5 now. And by the way, I already did my my docking checklists. Didn't want to bore you with that. Okay, so there it is.
Houston, we show capture and hard dock. Congratulations.
All right. Very good. Just give you a view here. Isn't that nice? International Space Station. So, as you can tell, that was actually pretty complicated. We had to get to be in orbit first. Of course, the video doesn't even cover launching from Earth or anything like that. That's a whole other thing. But once you're in orbit, you have to align your planes, and then you have to think about where your orbit is relative to your target, and then you need to synchronize your orbit by either speeding up or slowing down. And then as you're rendezvousing, you have to do a final burn to slow down, and then some final maneuvers to get in close enough, and then the docking procedure itself, which is going down that little runway. Okay, so that's pretty cool. We did that. And looks like the sun's about to go down. So like I was saying earlier, one of the things I like to do is get all hooked up to the International Space Station and just sort of for fun press all these buttons, opening the inner and outer airlock doors, which will allow people to come in and out of the spaceship, which is kind of cool. And then I can also charge up my various, this is my life support system, so there's various gases here, there's oxygen and nitrogen. And then over here, you can also open up a fuel hatch and then recharge your fuel system, basically. And so I'm going to try to get a full tank of gas, basically, in preparation for our Mars transit. So, but I think what needs to happen right now, while this stuff loads up, is I'll jump on the ISS and get a gin and tonic or something like that. Here they've got it stashed away, and then spend the night, and then we'll take off to Mars tomorrow.